Hey everyone. In today's video, we are going to be talking about friction. Friction is the last major subject that we're going to be talking about in the unit of dynamics, and it's definitely a big subject, so hopefully this video will give you kind of an overview so that you'll be able to solve questions that involve it that we do in this unit. So friction, we've already talked about it a little bit, and you remember that we looked quite a lot at the forces of friction, specifically forces of kinetic friction and the forces of static friction. And we described the difference, and we looked into this a little bit, and this was back in a previous video on forces. But one thing we never really stopped to think about is a couple things. One, what really is friction? We didn't really talk about it. And also, how do you actually do questions with friction? In all of the questions up until this point involving friction, either you've been told to ignore it, you've been told there is none, or you've been told exactly how much there is as an actual value in newtons, like, oh, there's 10 newtons of friction force, which is not a very realistic way to solve problems using friction. Usually this number is not what you're given. And so today we're going to look at what friction is and how we can do problems with it in a more realistic manner, and specifically something called the standard model of surface friction, which kind of is a mathematical model that encompasses all this, and we'll try and explain what that is and what we can do with it. So, friction. First off is really, what is friction? And the basic thing with what is friction is to think about it like a rubbing between two surfaces. And the only way that this really makes sense is if you look at something which is like really obviously rough, like sandpaper. Let's say we have two pieces of sandpaper. Here's one piece, here's another piece, and we're rubbing them back and forth, like it's going like this and this, back and forth, back and forth. If you ever try this, which probably not a great idea, but sure, you'll notice that there's quite a lot of heat that gets put into the atmosphere when you do this, and that heat is caused by friction. When you really put it simply, the gist of it is friction is a force that resists or prevents the sliding of two surfaces across each other. So if you have a surface and another surface and you're trying to slide them back and forth, or even just in one direction, what's stopping you from doing that at like infinite speed is friction. It's restricting your movement. Friction is so complicated that there's a whole field called tribology which just deals with it, which is why we're just going to go over the basics today. Now, there's a lot of different types of friction, and that basically depends on what materials are being slid across each other. And we learn in chemistry about solids, liquids, and gases, and you can have friction between literally any two of these. So here's solid, liquids, and gases. And you can have friction between solids and solids, liquids and liquids, gases and gases, but also any combination of these really that you want. But for us, we only need to deal with a very specific subset of these. We're going to look at solid-solid and solid-liquid. These are the most common types, realistically, especially solid-solid. In this lesson, we're going to focus on solid-solid, that is friction between two solid objects, and we're going to look at it using math. Solid-liquid we'll look at in other things, but more generally just kind of qualitatively, like, what is it, how does it work? But the solid-solid is really the main thing we are going to approach. One last thing it's worth highlighting before I get started is, why does friction actually occur? Like, what gives friction its existence? And that is basically the fact that even if you have two objects that you think are really smooth objects, it's actually a lie. If you zoom in on the object, you'll notice that there's really, at the molecular level, little grooves, almost like saw teeth, on every object, because just molecules are not perfectly flat. They cannot create perfectly flat surfaces. And it's these little kind of ridges back and forth which create friction. They interlock and they prevent you from moving. It's kind of intuitive, but it's just happening at the molecular level. so you really just do not notice it as much as you might notice if it was happening where these things were like visibly jagged. So that's really what friction is, and we call these little jags welds, and they're kind of the little molecular gaps between things that allow things to be so quote-unquote rough that they actually create friction. Now, another important question: what affects friction? We say that we can calculate friction. This means that there's values of friction, but what determines that value of friction? I mean, there's some very intuitive answers. For instance, pretty well everyone could tell you that, for example, sandpaper has a lot of friction, whereas ice has very little friction, and maybe cloth would be somewhere in between. We can all kind of intuitively tell you that, but why really is it? This has to do with really a lot of different things. In fact, there's so many factors, like I said, there's a whole field around it. But really, we start on two major things. Number one is the roughness of the surface, and number two is how much the surfaces are pushed together. So we're going to look at these two predominantly. Now there's a lot of other ones: how fast the object is pulled, the surface area in contact, the field strength, the mass of the object, and we're going to really ignore it all for the most part and just deal with something called the standard model of surface friction. Standard model. And this standard model is useful because it simplifies things to a degree that we can actually work with without making it unnecessarily complicated. According to the standard model, these two things are the only things which matter, except those stated in slightly fancier words. We call this the material type, because it's literally the type of material. Is it ice? Is it wood? Is it rock? Is it copper? And the other one is literally the force of the two objects on each other, the force pushing them together. What kind of force is this? Incidentally, it's a force we've already met, and that is it's a normal force. Remember, that is the contact force of one object on another. It's called a normal force. And that's really what we're dealing with when we say the force of two objects together. So depending purely on the material type and the normal force, we can get ourselves the standard model of friction. And this standard model of surface friction is what we're going to use. Alright, let's get a little more in detail here. What exactly is the standard model of surface friction? Well, I mean, it's a lot of things, but really it's a very simple equation. I'm going to write it right here. And then it'll look confusing, and we're going to explain it. This equation is the most important thing to understand about friction, assuming you know what it means. Let's break it down. First off, over here you have this. This is a force of friction. Notice I didn't put a letter here, and we're going to get to that. There is a difference between static and kinetic friction in the standard model, but the equation is the same for both of them. So whether there was a K here or an S here doesn't matter. Then we're dealing with this very special character here. This character is mu, mu, and is the Greek letter m. And we use it to represent a thing called the coefficient of friction. Okay, just threw a lot of words at you. Let's kind of break that down. The coefficient of friction is what we got from the material type. Different material types, and this affects both of them, so like the material type of the one object and the one you're rubbing it on, both material types factor into this magical value called the coefficient of friction. And the coefficient of friction, which I'm going to write here, coefficient of friction, has no unit, it's unitless, but it's measured and we just know it. We know it experimentally. Yes, there is complicated math behind how to get coefficients of friction, involves chemistry and biology and physics, and we don't need to worry about it because for our intents and purposes, we get to deal with this very special thing, which is a chart. This chart tells you the coefficients of friction for various materials. In questions you do, they will be on a chart like this, or given in the question. You will never need to figure out the coefficients of friction. You'll notice here there's two columns here. And that is because there is a separate coefficient of static friction and of kinetic friction. Also, some of these are ranges. We're going to get into more what they mean, but we're going to go back to here and notice that this question mark here, which was either an S or a K, also goes here. There is either the static or the kinetic coefficient of friction. This last one, we've met this symbol already. It is just a normal force. And that's literally what it is. The normal force between the two objects we're concerned for when we are calculating friction. Now the coefficient of friction has ways to calculate it, like I said, but we have a table, so we can really focus on what this equation does and how it works. Let's talk about the difference between kinetic and static friction, because we've said it a little bit. I explained it at one of the first videos, but not really in enough detail to be helpful. And I'm going to explain it with the help of a graph, which will make sense as I explain it, and probably not before. Okay, so let's start here. We talked about two types of friction, static and kinetic. And intuitively, we know what these words mean. Static just means staying. It means in one place, not moving. Kinetic means in motion. And that is literally how this works. But what does friction have to do with this? Now, the way we look at this is pretty simple. I'm going to go back to an example. Let's say you're moving houses and you have a box. A heavy box with, say, I don't know, some furniture in it. I don't know. But it's on the floor. So the two things which matter in this are this box and the floor. These are the two surfaces that we're taking into consideration. The box is obviously cardboard. The floor is, I don't know, let's say it's ceramic. So we have these two materials here, and we are interacting between them. Now, we know that there's a gravitational force on this box, because there's always a gravitational force, but also a normal force here, and this normal force, which is between the box and the floor, we might even call it the floor, is the normal force that's going to go into the friction equation, because it's indicating, as the standard model says, how much these two things are pushed together. So, we have the box and on the floor, and you're going to come up and you're going to try and push the box. So what's going to happen? Let's assume you don't really put a lot of pressure on it, and you try and push the box. What's going to immediately happen is the box is not going to move, because you did not push hard enough. So you're going to be like, okay, I need to increase my pressure. So you push with more force, you increase the force, and the box is still not moving. Now you're getting mad because you really need to move, so you push even harder on the box, and finally you hit some magical threshold and the box starts moving. Once it's moving, you'll notice suddenly the box is a lot easier to move. You don't have to maintain that initial hard push once the box is moving. That being said, what I'm saying is that it takes more effort to get something to start moving than it does to keep it moving. And that is the difference between static and kinetic friction. Static friction is preventing you from moving something. Once it's already moving, the thing that's limiting your speed is kinetic friction. Now, we literally use two separate coefficients, and it's just with an S and a K, just like we do the forces. And what we say about these forces is something interesting. Static friction force, which is this, involving that coefficient, is a variable force that self-modifies up to a maximum value. That is just a lot of words. That's not very helpful. What it's trying to say is that, basically, as you apply more force, it'll apply more friction force. Now, this is really confusing, so I'm going to try and take a little bit of time to explain this, because this is probably the most important concept in this whole thing. So, in this box example, I'm going to turn this into just a free body diagram. You have your box here, it has a normal force going up, it has a gravitational force going down. You're now pushing on it, which is giving it an active force to this direction. Now, common knowledge tells us, and we've already figured it out, there is a friction force going this way. And we're going to start with just static friction. The box is not moving, so there's a static friction force going in that direction. Now we learned something. Newton's first law and also kind of common sense tells us that, this box wants to stay at rest. And in order to move it, we need to give it a net force that's unbalanced. Now, ignoring the up and down, the y direction, just forgetting about it, we really have this direction here. And we're dealing with a static friction force which is opposing, it's opposite to this active force. This box is not going to move as long as the static friction force equals the active force, because then F net in x will just always be 0 as long as these two forces are equal. That's pretty intuitive. And it also makes sense. If the forces are balanced, Newton's first law tells us the box is not going to move. So, you start out, lightly pushing the box, applying 1 Newton of force. Well, the material responds by giving you 1 Newton of friction force back, and it doesn't move. You're like, okay, I need more force. So you apply 2 Newtons of force. The material just increases its force to 2 Newtons. This is what is meant by a self-modifying force. Static friction literally just accommodates however hard you push it. If you push it harder, it gives you more force back, keeping the box from moving. If you're like, okay, I'm giving it 10 Newtons, static friction is like, no problem, 10 Newtons back at you. And in all of these cases, F net x is staying at 0. But then something's going to happen. There's a critical point at which static friction is going to reach a maximum value. And this maximum value is dependent on the materials, and it's the point at which static friction stops functioning. Let's say that's at 15 Newtons for this random scenario. That's not true, but just for the sake of it. At 15 Newtons, all of a sudden, static friction is going to give up. This whole thing is going to break. Static friction can't give you 15 Newtons, so it won't. And all of a sudden, your active force has overpowered static friction, and the box is moving. Static friction here is going to be replaced by kinetic friction, which is a lower value, and it's going to stay constant as long as you keep moving the box. That is what this graph is attempting to show. On this side, we have the magnitude of the force of friction, which is being shown here in newtons. And on this side, we have time. This is assuming you just continuing to push on this box. At the beginning, you're putting very little force, absolutely nothing, and so it's returning you very little static friction force. As you continue to press harder and harder and harder and harder, this is going up. Static friction is increasing as your force is increasing so that the net force remains 0. And at this critical maximum value, that breaks down, we jump down, and suddenly we're here, moving the box, and we have a specific value of kinetic friction. Okay, so this is the difference between static and kinetic friction. When the object is not wanting to move, that's due to the static friction resisting the applied force. And if you keep adding force, eventually you're going to hit a point where the static friction will break down. And the specific point that is, by the way, is dictated by this coefficient. And it's the formula we had before, where we said that this coefficient times the normal force gives us the value. For static friction, it's actually giving us the maximum value, because static friction can be any value from 0 up to that value. But when we reach that value, it breaks down and it switches to doing kinetic friction instead, which is a very different thing and also simpler because it mostly just stays the same. Okay, hopefully this was all not too super confusing to explain how this works. We're just going to look at this chart in a little more detail now that we know what we know. A couple things to observe. First of all, you'll notice in practically every case, the coefficient of static friction is greater than the coefficient of kinetic friction, or at least the same. And that is because objects tend to want to stay put. This is for two reasons. One of them is Newton's first law, or the law of inertia, which we've already learned. Objects just really don't want to move unless you apply forces. Because of this, the force that you need to overcome to start moving the object is usually more than the force you'll need to keep it moving afterward. The second thing is this confusing concept called a mechanical weld or a cold weld, which is a molecular kind of physical chemistry concept where basically these molecules kind of want to weld together. Remember those little grooves, and stay together when they're not moving. It creates a stronger hold among atoms. This is not super important. The point is, static friction is always going to be greater than kinetic friction. And that's the case pretty much always. Now, usually, the coefficient of friction is a value between 0 and 1. This is not always the case. In fact, there's a couple places where it's like, no, not true. But overall, it tends to be between 0 and 1. Last thing is, why are there different coefficients for some objects where there's like ranges? Well, this is from 0.5 to 0.8. And the answer for that is just friction is complicated. Depending on the sunlight, depending on the heat that's on the surface, temperature conditions, depending on environmental factors, friction can change. The best we can do with the standard model of surface friction, which ignores all that, is to give you ranges. Don't worry, questions will give you values because we're just dealing with very simple facts right now. There is one last thing that has to be discussed when talking about friction, and that is how many exceptions there really are to this rule. We have our standard model of surface friction, which gives us this rule that the force of friction of something is equal to that coefficient times the normal force. And as with most things, this will make sense when we start doing word problems, which I promise we will do. But this little formula, and by extension, the standard model, assumes a lot of things. We're going to say that it assumes really three main things. There are three assumptions. And while we don't need to worry about them because they're ignored, we do need to know what they are to answer questions about the assumptions and to know what we don't have to factor in a question. The three assumptions are these. Assumption number one is that F is independent of area. Before I said that surface area is a factor of friction, and our answer to that in the standard model is don't care. We assume that it does not change dependent on the area. Exceptions to this are objects which are heavier in some places than others. If the object is not evenly placed on the surface, there's lots of them. We're not going to worry about any of them. Assumption 2 is that the force of friction is proportional, remember this operator, to the normal force. That means the more closely packed together these objects are, as you put normal force on them, friction is going to be proportional. There's going to be more friction. This is true for nearly everything in the world. If you put two pieces of sandpaper together really lightly and rub them, it's not going to be that difficult. If you press them together with a lot of normal force and try and push them, much more difficult. There are exceptions like spikes or things which are sticky, and we're going to ignore them all too. Final assumption is that the force of friction, I should have specified this is the force of friction. The force of friction ignores speed. In real life, the faster things are, the slower things are, it all affects friction. Things like air resistance, viscosity, which is kind of how like thick liquids are, all these speeds affect the friction. And as usual, because it's an assumption, we're going to ignore these things. So these three things can always be assumed to be true. We can always assume that the friction force does not care about the area, that it does not care about the speed, and that it is proportional to the normal force. So the more normal force, the more friction force, and vice versa. Finally, it's important to remember that the static friction is always greater than kinetic friction, which I mentioned already. And here's just a few facts just worth mentioning. There is static and kinetic, like I said, and we remember that the force of friction equals the applied force, this for a certain period of time, and then at some point when we reach this special value, which is the coefficient multiplied by the normal, when we reach that value, static friction breaks down and we switch to kinetic friction, and now force of friction is always less than the applied force, which we know because we're moving the object. Clearly, there's a net imbalance in forces. Alright, this was a big lesson. Friction is a complicated concept, and as you can see, there's a lot to it. Hopefully this gave you kind of some details on how friction operates. When we do real problems, we're mainly occupied with just that formula which we keep going over, which is over here. And that is dealing with the force of friction equaling the coefficient of friction times the normal force. In problems, the majority of the time, we can deal with this, we'll be given the coefficient already. We also need to be aware of the differences between static and kinetic friction and how that affects things. We saw this kind of confusing graph, and hopefully I did a good enough job of explaining how this graph affects the movements of things. You start by not moving, you apply more force until you hit the threshold, and when you hit that threshold, it switches to kinetic friction, and things start moving. We will, I promise, do real word problems where this will start to make more sense. But for now, this is really the gist of friction. And you can celebrate the fact that besides some word problems, this is the entirety of this unit of dynamics. We've now covered all that we need to know. Anyways, that was very long. Thank you for watching. Hopefully this was helpful to you, and I'll see you again soon.